Today we are beginning with another one of our lecture series, and this time we will be discussing about the analysis and design of steel structure in ETABS. So before beginning with the actual analysis and design process, today we will look at one of the features applicable which is present in ETABS, and that is the feature of section designer. We may be using this section designer feature while analyzing and modeling of steel structure in ETABS. So before actually starting the modeling process, let's go through this feature and see what it does for us. Section Designer is an integrated utility built into SAP 2000, CSI Breeze and ETABS. All of these are CSI applications that enables the modeling and analysis of custom cross-sections. So if you look at this form here, this form is a screenshot that I have taken from ETABS. When you want to define any cross-sectional property, then you go to define and cross-section and frame sections. Then you will be shown this frame property shape type. And here you can see there are some frequently used shape types such as rectangular, circular, this somewhat T section, and other sections for concrete. Similarly, for steel you have this I section, channel section, pipe section, tube section. These are the templates that is generally available in ETABS for defining different types of cross section. Similarly, for composite sections you have these 4 templates here, and there are some special sections that you can define from this special menu here. So here you can see section shape is concrete rectangular. If you click on this drop down menu, then there are different section shapes available, about 34 sections. So this is the template that is readily available in ETABS. We also looked at this non-prismatic section, how to define the non-prismatic section in one of our lecture videos regarding the design of pre-engineered building. So this auto select list we will be discussing and using this option in this design series also. So this is the template that is available in ETABS. What to do when you want to model a different type of section, an unusual or a different type of section that may not be available in ETABS. Suppose that your architect gave you a house plan in which they have used somewhat this shape of column here. So this shape of column or this template of column does not match with any pre-existing template in ETABS. So what to do in that case? We will use this option of section designer. So if you go to our previous slide, section designer enables us the modeling and analysis of custom cross sections. So not only the modeling, the section designer, once we have modeled our custom cross sections, then it gives us some very important properties of that cross section also. And the first is the cross sectional properties. And these cross sectional properties may be of various types. They may be the center of gravity, the moment of inertia, the shear area of our cross sections, or these cross-sectional properties may even be some design data like radius of gyration, section modulus, and plastic modulus. So the first analysis result that a section designer gives us is the cross-sectional properties of the cross-section that we have modeled in section designer. Similarly, section designer also calculates the moment curvature relationship for a cross-section. You may have learned about this moment curvature. Curvature denotes the extent of bending that is present in any cross section, may it be a beam or column. You may have studied if this is a rectangular beam, and if we want to draw the strain profile, then here will be that 0. This will be the strain profile. So if you suppose that the strain at the extreme compression fiber is epsilon, and then the depth of this neutral axis from the extreme compression fiber is C, then the value of our curvature is given as epsilon over C. So if you draw the curve representing the relationship between moment and curvature, then you may get some different types of curve for different type of material. And once you have got this moment curvature curve, then you can calculate the yield moment, and then you can compare it with the ultimate moment capacity or the moment that comes onto your cross section also. So besides cross-sectional properties, section designer also gives us the moment curvature relationship for a cross section. And finally, what it gives is it also gives us the axial flexural capacity of a cross section. Remember, in one of our design series on design of residential buildings, there we talked about the PM interaction curve. So if you plot the axial force on this y-axis, and suppose that for our column there is only uniaxial bending, that is only M3 moment, and if you draw a curve, then you get this failure surface. So the points on this curve represent that combination of axial load and bending moment which causes the failure of that particular cross section of our column. So this surface is known as, or this curve is known as interaction curve. If your column has biaxial moment, that means both M3 and M2, and if you draw the curve or interaction curves for these three loadings, that is the axial force and the two moments M3 and M2, then you get many interaction curve that form a surface, and that is known as the interaction surface. So that interaction surface is again a failure surface, which gives us the value of the combination of these three loadings that causes the failure of our column. Since section designer also gives us this PMM interaction surface for our cross section, and from that PMM interaction surface we can calculate the axial flexural capacity of our cross section. So these three are the important information that section designer gives us once we have modeled our custom cross sections in section designer. So we have looked at this frame property shape type. So here are different types of cross section based on material and geometry. If you look at this slide, then these are some of our custom cross sections for which the template is not available or may not be available in ETABS. For example, you can see here this built-up section is composed of two angles and one C channel. Here is another composite section, here another composite field section, and different other types of section based on material and geometry. So all of these custom cross sections can be modeled in section designer, and the important information can be extracted for our cross section. So this is the general introduction to the section designer. We will look at ETABS, so how to go to this section designer option and how to model. Here is a simple window of our section designer. We have different selection tools here, different drawing tools, and then you can some zoom features, editing features, and then there are these three options which is also available under this display tab. These three options are the important information that the section designer gives us that we just discussed. One is the cross-sectional property, another is the moment curvature relationship, and another is the axial flexural capacity of our cross section. So this is the canvas on which we model our cross section here. And today we will be looking at two examples. First, we will be drawing this trapezoidal beam in our section designer, and then we will look at the important parameters or important information that we can extract, and then we will draw this composite column here, this built-up column, and we will be drawing this similar type of built-up column in our design lectures also. Today we will just be looking at how to draw this. First this trapezoidal beam here, and then this built-up column. So first let me go to ETABS and open a new model. So I have already opened ETABS here. I will just click on new model. Then I will begin with a new model here. So let me use built-in settings with. I will use these same options here: metric SI units, Indian steel section database, and Indian design codes for both steel and concrete. So here, let me begin with this flat slab type system, although we do not need this. This is just to begin the model. Just I will click OK. I will click OK here. So this model now appears on our screen here. Let me just change the graphics mode. Okay. So let's go back to our presentation, and you will see here that we have one trapezoidal beam here, and this trapezoidal beam has a top width of 400 mm. So this is the top width, depth of 500 mm, and this depth means, according to this figure, the depth from the top to the centroid of this reinforcement bars, and then the width at the level of reinforcement bar is 250 mm. Since I took this example of a trapezoidal beam from one concrete design book, so the total depth is not mentioned here. What we will assume is that the distance from this bottom surface of the beam to the centroid of this reinforcement bar is 35 mm. So the total depth will be 500 plus 35 is 535 mm, and then if you assume that we have been given that the width at the level of reinforcement is 250 mm. Okay, let us just ignore this and focus on this beam here. We have the top width 400 mm, the bottom width 240 mm, and then the height of this, or the depth of this beam, is 535 mm, and then the reinforcement area is 1473 millimeter square. That means we have used here 3 rebars of 25 mm diameter. If you calculate the area, you will get this total area if you use 325 mm diameter bars. The characteristic strength of concrete is 25 megapascal. This is the grade of concrete, and the grade of steel is 415 megapascal. So what we will do is, we will first define these materials first for both concrete and steel, and then we will go to section designer to model this element here. So first, to define the materials, you already know, go to define material properties and add new material. The region is India, material type is concrete, and the grade of concrete is M25. Click on OK, and then again click on OK. So this M25 appears on our list of materials. Again left click and add new material. This time the material type is rebar, and the grade is grade 415 is already selected here. Left click on OK. The properties of this 415 grade steel is given here. Again left click on OK. So we just need these two materials, and then left click on OK again. So we have defined our materials. Now to actually draw the model, what we will do is, we will go to define section properties and frame section. There are some already defined list, this default list of some properties. We will go to add new property and left click on it. So this is the form that we discussed in our slides. If you click on this drop down menu, here are different shapes for both steel, concrete, precast, cold form steel, and other sections here, about 34 shapes. And these are the generally used shapes for our concrete, steel, and composite models. So here we have the option section designer. We will left click on this section designer to create a custom cross section of our own. I will name this property as trapezoidal beam. You can rename the property according to your wish. The base material will be M25 concrete. And then after applying this base material. The design type for now, just leave it as no checker design. And finally, go to this section designer tab here and left click on this section designer tab. Now you are presented with a model or the canvas of our section designer. Here you can see there are grids on this canvas here. The x and y axis is given as shown in the canvas. This is and this x and y axis, it overlaps with this y axis overlaps with the 2 axis, and this 3 axis is in the opposite direction of this x axis. So these 2 and 3 axes are the local axis of our cross section. So to model this, just remember for now our top width is 400 mm, our bottom width is 240 mm, and our depth is 535 mm. So what we will do is, if you go to this draw option here, you have different options for drawing sections of steel, concrete shape. In steel you can see you have I or wide flange, channel, T, angle, tube, pipe section. In concrete you have this rectangular, circle, T shape, L shape, and different other section. And then you also have the option to draw rebar. If you want to draw a single rebar or a line rebar, or you can draw the rectangle bar, for example in your beams and your columns. You also have the option to draw circle bar. And then there are other different options here. So to draw that trapezoidal beam, what we will do is, since there is no any direct draw option for trapezoidal shape, first we will draw reference points here. For example, go to draw a reference line and then point here. I will draw a reference point at the origin here. I will just left click on this and then a reference point 1 is drawn here. So let's just click on OK. So after drawing this reference point at the center, I will draw a reference point. For example, what I will suppose here is that I have drawn a reference point. If I suppose that this is our axis, I have drawn a reference point here. Now I'd like to draw a reference point for this top surface and this for this bottom surface. That means at a distance of 535 divided by 2 for both top surface and bottom surface. So that means 535 by 2 means 267.5. So just select this reference point here by clicking on this reference point and then go to edit and replicate option. So I will first replicate it in the y direction, in the upward direction, so positive 267.5, and left click on OK here. So this reference point is replicated here. I just zoomed into these grid lines here. Again select this reference point, go to edit, replicate. Now I will replicate it in the downward direction, so minus 267.5, and then left click on OK. So after that I want to draw these two edges here. So from the center, these two edges will be at a distance of 200 mm. And similarly for the bottom surface, these two edges will be at a distance of 120 mm. So just select this reference point, go to edit, replicate. Now I have to replicate in the x direction, so dy will be 0, dx will be first positive 200 mm. Okay. Again select this reference point, go to edit, replicate, and minus 200 mm, and then left click on OK. So this is now our top surface of our trapezoidal beam. Similarly, select this reference point here, go to edit, replicate, 120 mm. So this is drawn here. Again select this reference point, go to edit, replicate, and then minus 120 mm. Okay. So now we have gotten the reference point for our trapezoidal beam. Now I will draw a polygon shape to form a trapezoidal beam here. So just click on this draw concrete shape on your left side, or you can also go to draw concrete shape and then polygon. So I will start by left clicking on this point, and then I will go in order to draw a trapezoidal beam. And to complete this beam here, I will just double left click here. Now you can see that our trapezoidal beam has been drawn here. After this, I want to add reinforcement, and you can see that here our reinforcement is at a depth of 500 mm from the top. That means our reinforcement will be at a depth of 35 mm from the bottom, and we have 3 25 mm diameter bars. So for that, I will just select this reference point here. Sorry, I selected this reference point. I will just replicate this reference point to draw the line for our reinforcement, and I will replicate in the upward direction at a distance of 35 mm. So dx will be 0 and dy will be 35 mm, and then click on OK. So this is the line where our reinforcement will lie. To draw reinforcement, either go to this draw rebar shape or go to the draw option. I will just left click here, and then what I want to draw is I want to draw line rebar, not a single rebar also, not a rectangular rebar also. Rectangular rebar means, for example, if you have this column here and you want to draw a rebar on all this side, for example 1 2 3 4 5 6 7 8. If you want to draw this all of these 8 rebars, then you have to select this rectangular rebar. But for now, I just want to draw a line rebar here. So left click on this draw line rebar, and our line rebar will lie along this line. So I will just create a line here, and you can see that one reinforcement has been placed here. Now to edit this reinforcement value, what to do is just left click on this line, and this rebar line will be selected, and then right click here. You can see section object data form appears here. First, what we will do is we will change the material of this rebar to HYST 415, because this is the material that we are using. This rotation option, you can see here, this line may be rotated while drawing, so this rotation chooses 0 degree here. Other, you may or you may not want to change also. If you want to know what this x1, x2, x center means, just left click on this option and read the description at the bottom. The x center means the x coordinate of the center of the line. This length means the length of the line. So in this way you can see the description here. Now for rebar, what I will do is first I will change the bar size to 25 mm, and the number of bars is 3 here. This has end bars. If you change this option from no to yes, then these end bars will be created at the very end of this two ends of this line also. So I will just leave the option as no, and then left click on OK. You can see that now our 3 rebar of 25 mm diameter has been completed here. So after the completion of your modeling, then you do not have to perform any type of analysis here. It's already performed. You just have to see the results here. So first, either I can go to display and section properties, or you can left click on this table here also to see the section properties. Remember that in our slides we discussed that 3 types of important information are displayed by the section designer. One is the section properties, another is the moment curvature curve, and another is the interaction surface. That means the axial flexural capacity. So if you left click on this section properties, now section properties is displayed for this cross section here. In section properties, you have this center of gravity for x and y direction. You have some analysis properties like cross-sectional area, shear area, and then this moment of inertia and this torsional constant. Similarly, you have these design properties like radius of gyration and the section modulus, the plastic modulus, the principal axis, and you have this major principal axis moment and minor principal axis moment, and other different types of cross-section properties are being obtained here. See here, orientation of two axes for these properties. If you want to obtain these values based on the principal axis, then you can check this principal axis and then this value change here. Or you can give your own angle. If your bending angle or bending axis do not coincide with any of these default axis or principal axis, you can just select this user and then you can give the angle from x to 2 axis. And if you suppose I give an angle of 45 degree and then click anywhere, these values will change. So for now, selecting this default means your bending axis in your actual model coincides with the default axis of our cross section here. So in this way, you can get the cross-sectional properties of a cross section. I will just click on escape. Similarly, now I want to see the moment curvature curve. So I will go to display and then left click on moment curvature curve. So this is our moment curvature curve here. So I said this is some general diagrams of moment curvature curve previously. You can see that at the very beginning there is a very little increase in curvature as there is an increase in the moment, and at some point in this graph your steel reinforcement bar starts to yield, and as they start to yield the curvature gradually increases. So the importance of this moment curvature curve is that you can find your yield moment here and then you can apply any external moment coming onto your structure. You can compare the yield moment of your cross section and the external moment coming onto your model or coming onto your cross section, and then you can compare those two moments to see if the cross section withstands our external moment. So this is our moment curvature curve for this cross section. And remember that moment and axial force in our cross section always interact. So for example, if you see here, the yield moment is in the range of 240 to 270 kilonewton meter. If you increase the axial force in your cross section, for example, currently the axial force is 0 kilonewton. If suppose that 50 kilonewton cross axial force comes onto your cross section, then you can see this moment curvature curve changes. If you again increase your axial force, again this moment curvature curve changes. So in this way, you can also provide the axial force to see the interaction between this moment and axial force, and also the angle of your cross section. Similar to what we discussed in cross-sectional properties, if your bending axis does not coincide with the axis of your cross section, then you can provide the angle between those two axes. So this is the curve, and if you want to see tabulated values, then you can left click on the show table and you can either export this table to Excel here from this option, or you may just look at the values from this table also. So in this way you can check the moment curvature property of our cross section also. And finally, to see the interaction curve or this interaction surface, left click on this option here. Now you can see the interaction surface here. You can either see the full 3D view of this interaction surface or the interaction curve for PM3 only or for PM2 only. And you may want to include the material strength reduction factor or exclude the material strength reduction factor. These reduction factors are given in your code, design code. So if you see the curve here, and if you select this exclude material strength reduction factor, then this curve changes a little. You can also superimpose the dashed fiber curve from this option here. So I will not go into detail about this. You can see the various combination of PM2 and EM3 that causes the failure of this surface. And this becomes important primarily when you are using this cross section as a column. In this way, you can determine the axial flexural capacity from this interaction surface for your cross section. So this is about the important information that the section designer gives us after the modeling of our section in this section designer canvas here. So this completes our first example. This second example, let's do it, or let's learn how to model this built-up column during our modeling class also. You may want to practice this by yourself also. For example, if you see here, we have these two C channels here which are built up in such a way that they are face to face. And then these two C channel section, which are ISMC 300 channel, these two are built up by placing 6 mm thick pattern plates here on the both sides. So this outside boundary is for the base plate. We will not go into this. You can just practice modeling this built up column section by yourself also, and we will see into detail about how to model this during our modeling class itself. So to draw this steel built up section, you can just go to option here, draw I section, draw channel section. You can draw first two channel sections and then keep them face to face by orienting their directions, and then you can draw this plate for our 6 mm thick pattern plate. We will go into detail into this modeling of this custom or built up column section in our modeling classes. So this brings us to the end of our lecture for today. In another lecture, if there are not any topics to be discussed before actually starting the design class and steel structure, we will go into that topic. If not, then we will start with the modeling of our structure, first by looking at our architectural plans. So we will meet again very soon. Stay tuned. Follow our YouTube channel, Inquisitive Engineer. You can also follow us on Facebook. We have the same Facebook page name also, Inquisitive Engineer. And then keep posted and stay safe. We'll meet again soon. Thank you.